everyone, and welcome to week 4 and the module of the ozone layer. This week we're going to really lay a foundation about atoms and how to draw structures of molecules. And that is actually really important because it will help you better understand the next week's lecture. We're going to really focus on the ozone layer in next week. So for now, we're going to lay that foundation this week. If you would like, you can go ahead and move directly into week 5. Both modules should be open. All right, well, let's get started on the first lecture. So first of all, let's talk about what atoms are. Matter is really anything that makes up space and has mass. So for example, your table or your house or the food you eat or the air you breathe, it all has mass and it all takes up space like a volume. And all matter is made of atoms. The analogy that I would like to make is that if you had a house, the bricks would make up the house, and for this would be the atoms make up matter. Now, a question you might be asking yourself is, what is the difference between elements and atoms? We previously had discussed about the elements in the periodic table, and elements were described as the building blocks of all matter, just like we described atoms being the building blocks of all matter. And one way to think about it is that elements are made of atoms, and I do have an ice cream analogy for you. So for example, say that you go to Baskin-Robbins or whatever ice cream store you like, McConnell's, whatever, and you see the tubs of ice cream and say they're all just each one flavor, like vanilla, for example. And that whole tub of ice cream is vanilla. That's your element, vanilla. And if you were to take a scoop of the ice cream, say the smallest unit possible you could get at the ice cream store is a scoop of ice cream, one scoop. That one scoop of ice cream would be your atom. So an atom is the smallest amount of an element. Another way to look at that is, for example, you have carbon. Here is your pencil. The lead pencil is carbon. It's actually a structure of graphite. It's a bunch of carbon carbon atoms bound together in a structure. So it's carbon atoms over and over and over again. So you have this large amount of element, but really the atom is carbon. And same thing, you can have a gold bar, which is a bunch of gold atoms structured together. And atoms are really tiny. I'm sure most of you already know that. And if you were to actually take the diameter of a single human strand of hair, this would be your diameter. And if you were to take 1/1000th of that single strand of human hair, this is the size you'd have. 1/10,000th would be this, and 1 micron. If you actually zoom in on that 1 micron, you get again another circle here. And if you were to do the whole thing again, you get this little tiny dot. And that dot really is 1 nanometer. Okay, that represents 1 nanometer. And that's the units we use for atoms. So you can already see it's significantly smaller than your single strand of hair. And the other unit we use for atoms is an angstrom. Right here is given as 1 with a little circle on top A. And that's actually 0.1 nanometers. Atoms are typically 1 to 5 angstroms. And so if you actually look at that little dot, 1/5 or 1/10 of that dot is an atom. So the takeaway message here is an atom is 1,000,000 times smaller than the thickest human hair. And we're actually able to image atoms using scanning tunneling microscopy, or STM. This was Nobel Prize work by IBM. It was created in the 1980s, and I actually did research in graduate school using this instrument. It was really challenging but rewarding. And so what actually happens, you have this tip here, this like metal tip, and a surface that you're doing research on. And the tip runs along the surface of your sample, going back and forth, and you actually have a current that reads the surface. Okay, it's a very simplified way of talking about it, but that's basically what's happening. Is you're looking at a topographical map of the surface. You're not actually looking at colors or things like that. It's just you're seeing how tall things are and how low down or whatever they are. And we can actually see these atoms, but we can also manipulate them as well. And you can see that these are a bunch of iron atoms on top of a copper plate. And we can actually push the iron atoms along until you can get a circle. Or you can do something similar with xenon on nickel. Here is another example. IBM actually wrote their own name out. So now you have an idea how small atoms are and how we're actually able to image them. I'm going to talk to you about the current nuclear theory. And what you see here is a very simplified version of what an atom would look like. So we have, an atom has three basic components: a proton, which is has a positive charge, known as proton and positive. They both start with P's. That's right here in the center. You see a positively charged particle. And then you have a neutron, which has no charge, and that's this orange particle here. Again, neutron, neutral, they sound similar. And the electrons are actually out here, and they have a negative charge. So this bulky stuff in the center with your protons and neutrons is actually called the nucleus. This whole center part is the nucleus. The electrons are not part of the nucleus. They actually orbit around the nucleus. And most of this atom is actually empty space, and these electrons are really tiny. And to give you an idea of how tiny those electrons are, I'm going to show you the masses here. So if you look at the mass of a proton, you can just look at the atomic mass unit. It's about 1. A neutron is about 1. So the proton neutrons are almost the same in terms of the mass. The electron is 0.00055. So the electron is significantly lighter. So most of the mass of your atom is actually from the proton and neutron. And if you were to do an analogy, this baseball here would represent your proton, and this grain of rice would represent your electron. So most of the atom's mass is in the nucleus. So it says here the nucleus is 25,000 times smaller than the atom, and if the nucleus were the size of a raisin, the atom would be larger than a sports stadium. So even though, again, all the mass pretty much, or most of the mass is in that nucleus, there's a lot of space that the atom has, and that's where all those electrons are in. The other interesting property about the atom you should be aware of is that there's the same number of protons and electrons. And this is just because matter is typically charge neutral. Okay? They're not like magnets. You don't have your chairs trying to stick together, or things are not flying around in space landing against the wall, stuff like that. I mean, things are charge neutral. They're not like magnets. And so what that means for you is that if there's a positive charge, there must be a negative charge to cancel out the charges. And the way to think about this is that opposites attract. So positive and negative electrical charges attract each other. Like this picture here, we have the red is a positive and the negative is a yellow. They join together, and when they join together, they actually cancel out the charges, and you get so this positive plus 1 plus a negative 1 gives you a 0, so those charges cancel each other out. If you were to have the same charge, like a positive and a positive, or a negative and negative, they would actually repel each other. Like this picture of like the magnet where this kid's trying to put it together and it just keeps repelling. The other interesting thing you should be aware of is that atoms usually have about as many neutrons as protons. Notice the word usually, not always. Here, this one is usually. So, for example, with a hydrogen, we have 1 proton and 0 neutrons. Right? It's not the same. Helium, you have 2 protons, 2 neutrons. So this one's easier. It's the same. And carbon, you'd have 6 protons and 6 neutrons. But notice in each of these examples, you have the same amount of electrons as the protons. You have a 1-to-1 here, 2 protons, 2 electrons, 6 protons, 6 electrons. So the other takeaway message from this, and we'll talk about isotopes later, don't worry about isotopes, is that the protons is what defines your atom. Okay? So if you add a proton, you put a proton here, you have now helium. So 1 proton was hydrogen, 2 protons is helium. Now all of these elements or atoms are arranged in the periodic table as we talked about before. And if you were actually to look at the periodic table, there's a bunch of numbers here. So you could zoom in on any of these. I'm going to show you oxygen. The top number here, 8, is the number of protons, also referred to as the atomic number Z. And again, that number also will tell you the number of electrons. You should have how many electrons? 8, right? You should have 8 protons and then 8 electrons. And 8 is a special number. It also identifies oxygen. If I tell you there's an element in the periodic table that has 8 protons, you could right away know that's oxygen. The O is the element symbol. It's an abbreviation form of the element. The element's name is oxygen. And 16 here is the atomic mass and weight. That's just the number of protons plus neutrons. I'm going to highlight this for you. Again, the number of protons in the nucleus of an atom identifies it as a particular element. If an atom has a different number of protons, it would be a different element. Okay, to give you an example of how this would work, this atomic mass weight, I know I have 8 protons, it's given to me above, plus neutrons equals 16, right? Because again, the mass of the nucleus, the atom, is mainly the protons and neutrons. So I can actually find the neutrons based on that fact. So if I rearrange, I would have neutrons equals 16 mass minus 8 protons. That would give me 8 neutrons. All right, well that is the end of this lecture. I hope you enjoyed it. We will go ahead and get started into more background on atoms and bonding molecules together. All right, I'll see you guys later. Bye-bye.